Welcome to Ask and Learn.
For this question, we are treating the heat capacity for copper to be a variable, right? It changes over the different temperatures. I want to find what is the amount of heat required to raise the temperature of 2 kilogram piece of copper from 20 degrees Celsius to 250 degrees Celsius. So I given this is the empirical formula. Now this formula has our temperature in terms of kelvins, right? So we're gonna convert this into kelvins just in case, right? So this 273.15 plus 20 degrees is 293.15 kelvins. To 523.15 kelvins. So this is the temperature limits that we are trying to find. Now, considering it's a very specific temperature T, somewhere in between, some unknown T, we want to find what is the amount of energy required to raise the temperature of this copper by a small amount of temperature delta T. Right, so the amount of energy, small amount of energy, we call it delta E, be equals to m times C times delta T. Right, because we just want a small change in temperature at a particular certain temperature T, and we want to find out what is the small amount of energy required, or small amount of heat that is required. So this is the formula. Now to find out the total energy, we have to just integrate this. Right, we just have to integrate. On the left hand side, integrate with respect to the energy. So we have the initial energy, which is basically 0, and the final energy E. On here, the temperature we will integrate from 293.15 all the way to 523.15. Right? So the total energy required be m times alpha plus beta t plus delta t to the power minus 2 dt. So doing this integration should be quite straightforward. We just have 3 different terms. So for the first term, we just add 1 power of t. For the second term, we will take beta divided by 2 times t squared. And for the last one, we have negative delta t to the power minus 1. Alright, and the limits is 293.15 and 523.15. Mass is given to be 2 kilograms. So this would be 2 kilograms multiplied by the stuff that's inside. So the first limit that we're going to put is t is equals to 523.15. Right, so we have alpha 349 times t plus beta, which is 0.107, divided by 2 times t squared, minus delta 4.58 times 10 to the power 5 divided by t. Then we subtract away the lower limits, which is when T is equals to 293.15. Alright, so this is the answer that we should get in terms of the SI units, which will be in terms of joules.